Hey, welcome back. Today we're going to look at Unit 6, which is energy types. We will look at the major ones. We'll do so by viewing a video clip and then kind of recapping at the end with a very simplified version of the pros and cons of each energy source. So we will start with fossil fuels. Please stay tuned and watch this video. So coal is located pretty abundantly in the United States, which is why we've seen that we've used it over time. But China has actually increased its use since the 50s. It is good because it provides jobs and we have it here and it's cheaper, but there are a lot of bads because there is a lot of pollution produced when it's burned. And there's a lot of land destruction because of surface mining, and if the wastewater enters the streams, then it can lead to acid mine drainage, which leaches out a lot of really great ions in the soil, and also the inhaling of that soot can really damage miners' lungs. Alright, so as far as where oil is, you can see there's a lot in Saudi Arabia, some in Canada, tied up in sands and things like that, but we use a ton. So we are relying on it. It does provide a lot of jobs, and we do have some here. We're used to having an abundant supply. We use it in our everyday products. But when it's burned, it does release a lot of pollutants, and aquatic environments are at risk for oil spills. There is some land destruction, and you do have to use a lot of water, especially the oil we're talking about in Canada. All right, so natural gas, there's a whole lot in Russia. We have a lot in the United States. We like it because it provides jobs and it does release less CO2 than our other fossil fuels. It is a lower cost of energy and it can be used to power vehicles, although we don't have enough fueling stations to make it widespread. There is a release of methane, which is more efficient at trapping in heat, and there has been some correlation with when we are fracking near fault lines, earthquakes, and sinkholes. Resulting in, bottom line, it is still a non-renewable resource. Right, now onto nuclear energy. Watch these clips and then we'll recap at the end.
Howdy there, atomic children. Trace here for D-News. Despite the controversy they often raise, nuclear power plants are a huge source of our energy. The Environmental Protection Agency says nuclear power accounts for about 20% of electricity production in the U.S. One of the reasons why is because it's the most efficient means of extracting energy from a fuel source, about 8,000 times more efficient than coal or oil. According to the Nuclear Energy Institute, a fingertip-sized pellet of nuclear fuel contains as much energy as 17,000 cubic feet of natural gas, 1,780 pounds of coal, or 149 gallons of oil. Nuclear energy comes in two flavors, fusion or fission. Fusion is when two hydrogen atoms fuse. This happens in stars. And fission is when large, heavy atoms are broken apart. Both release energy, and both have pros and cons, but so far, we've only figured out nuclear fission. So when I say fuel, I'm talking about fuel for nuclear fission. Nuclear fuel is commonly referred to in the news as highly enriched uranium, but getting it to that point requires a lot of effort. And
it's a technology that we've been using for decades that can really reduce global warming. But it's not exactly something environmentalists are that excited about.
The first thing many people think of is nuclear war and mushroom clouds. You add into that major events like 3 Mile Island and Chernobyl and most recently Fukushima, and those have had incredibly profound consequences on people's immediate feelings and images and associations with this technology.
This isn't something where the public has the view wrong. It is a technology with a reputation that's been earned. However, as a conservationist, that makes me feel really conflicted because these power plants don't emit CO2, and that's the main pollutant that's causing climate change.
When you look at the technology and you ask yourself, how are we going to solve this problem of climate change? To not have nuclear energy be on the table makes the job much harder.
Now, for the most part, these plants work really well. They supply about 20% of the electricity on the US power grid. But almost all of them in the US were built over 35 years ago. In fact, they look like something out of a vintage movie set. And historically, they've had two big problems. They produce radioactive nuclear waste, and they can be vulnerable to a disaster like a nuclear meltdown. Nuclear meltdowns happen because water that's used to cool the radioactive fuel rods can't be pumped in, usually due to something like a backup power failure. This fuel heats up rapidly, and since these reactors operate at high pressure, there can be explosions from all this excess heat. You can think of it like a balloon popping and releasing the air inside, but in this case, radioactive air.
Okay, one thing to be said is that you still have to mine for uranium. It does provide jobs, much lower CO2, and lots of energy, but there are those other risk factors like meltdown, and the water that enters the waterways is actually heated up, and we call that thermal pollution, and of course the waste that can last for thousands of years. Now we're going to look at hydroelectric energy, and this video recaps the pros and cons at the end, so then we'll just move on to the next energy source once it finishes.
But today, modern hydro plants produce electricity using turbines and generators. The mechanical energy created by moving water spins rotors on a turbine. This turbine is connected to an electromagnetic generator which produces electricity when the turbine spins. There are two main types of hydroelectricity production: dams and run-of-river. Hydro dams utilize the potential energy from dammed water to produce electricity. A dam is a large barrier constructed to raise the level of water and control its flow. The elevation created by the dam creates gravitational force for turning the turbine when water is released. Some dams also contain an additional reservoir at their base where water is stored to be pumped to the higher reservoir for release when electricity is in demand. This is referred to as pumped storage hydro. The second form of hydroelectricity production is run-of-river hydro. Run-of-river still uses turbines and generators, but relies on natural water flow rates of rivers, diverting just a portion of the water through turbines. Because run-of-river hydro is subject to natural water variability, it is more intermittent than dammed hydro. There are various sizes of hydro plants that produce electricity. Large hydro, greater than 30 megawatts, small hydro, 100 kilowatts to 30 megawatts, and micro hydro, less than 100 kilowatts. The Hoover Dam in the United States is a whopping 2,074 megawatts, which is enough to serve 1.3 million people. Of all renewable energy sources, hydropower holds the largest share of worldwide electricity production. Hydropower has several benefits. It is a cost-competitive form of electricity, even though the initial building cost can be high. It is quite reliable compared to other renewable options and pairs well with other sources as it can be used as baseload power. In some cases, dammed reservoirs can also help with flood control and be a reliable water supply for communities. There are also some concerns with hydropower, especially when it comes to large dams. Damming a river has a major impact on the local environment, changing wildlife habitats, blocking fish passage, and often forcing people in riverside communities to move out of their homes. In addition, dam failures can be catastrophic, claiming the lives of those living downstream. Hydro plants are also not completely free of greenhouse gas emissions. As with most forms of energy, carbon dioxide emissions happen during construction, particularly due to the large quantities of cement used, and plant matter in the flooded areas makes methane, another greenhouse gas, as it decays underwater. That's hydropower.
Alright, now you're going to watch a video over hydrogen fuel cells, and we'll recap at the end, and you'll see it actually is an old technology.
In fact, they're really not that new. Fuel cells were invented in 1839 by William Grove and were developed by Pratt & Whitney and other companies in the 1950s. Safe and dependable, they were used by NASA and the Russian space program to power spacecrafts. Today, leading global companies like Apple, Verizon, and Coca-Cola use fuel cells to generate clean power. Honda, Toyota, and other car companies use them to power their new generation of pollution-free cars. So how do fuel cells work? Fuel cells use hydrogen and oxygen in a chemical process to produce electricity and heat. The only byproduct, pure, clean water. A fuel cell has two electrodes, an anode and a cathode, and between them, an electrolyte. The catalyst on the electrode breaks the H2 hydrogen molecules to allow them to combine with hydroxide, OH negative ions, to create water and release electricity. But unlike batteries, fuel cells don't store power for a limited amount of time. They generate it for as long as you have hydrogen. As a source of backup power, fuel cells are much better than diesel generators. They aren't smelly or noisy, and they don't produce harmful exhaust. Fuel cells can be used anywhere you need backup power. Mobile phone towers, electrical substations, manufacturing, and much, much more. Other green power solutions harness the sun or wind. But if you're caught up in a cloudy day or on days where the air stands still, these solutions can leave you without enough power when you actually need it.
So the byproduct being water is a great thing. It's super efficient. It can be renewable, but currently the way it's made, it is not. And we do not have refuel stations, and it actually is very expensive to transport because it has to be under pressure. So that's why it is not more abundant. Okay, so geothermal energy is both using what you can do at home, like heated water, or actually a power plant. And so watch this video, we'll recap at the end.
Or the geysers at Yellowstone National Park, you've seen geothermal energy in action. The Earth's crust is made of rocks and water. Deep below that is a layer of hot, molten rock called magma, which is even hotter than the sun's surface. The heat just over 6 miles below the surface contains 50,000 times more energy than all the oil and natural gas resources in the world. Releasing a small amount of that heat in the right way can create electricity. A well drilled a couple of miles deep can capture the rising hot water and steam. That steam spins a turbine, and a generator produces electricity. Geothermal is one of the least explored sources of renewable energy in the US, and most of us probably don't spend much time thinking about it. But since it's a pollution-free, renewable source of energy that's consistently reliable, at least it has been for the past 4.5 billion years, maybe we should.
Geothermal power plants rely on crust thickness and availability, so location is sometimes hard to come by, but if it's the right location, then it'll make sense because it is a high initial cost. It does use a lot of water, but it can prove to be efficient. If you use it in your home, then basically you have pipes underground and they go through your walls or your floors to help warm or cool your home. So biofuel is using anything that was once alive in whatever means that is, whether it's burning or maybe you have to ferment or maybe it's oils from algae, and so watch this video. So biofuel in moderation, because all living things require water. It does use water. It does compete for food, for whether it be feed or for us to consume. Okay, this video also recaps the pros and cons, so we'll just move on once it's over.
Speeds vary based on geography, topography, and season. Because of this, like other renewables, there are some locations better suited for wind energy generation than others. In fact, there are optimal wind locations both onshore and offshore. Energy is derived from wind by converting the air's motion into mechanical energy. Traditionally, this energy was used for milling grain and pumping water, but today is most commonly used to create electricity. The mechanism used to convert air motion into electricity is referred to as a turbine. A turbine is a large structure with several spinning blades, usually 3. These blades are connected to an electromagnetic generator that generates electricity when the wind causes the blades to spin. Wind is becoming an increasingly important part of the global electricity supply mix. A major advantage of wind is that the production of electricity has no direct CO2 emissions. But wind generation is not without its challenges. As everyone knows, the wind does not blow all the time, causing intermittency issues for power grids. The price tag of wind power has traditionally been higher than conventional electricity generation sources, though the wind cost curve has declined significantly in recent years. NIMBY concerns such as land use, noise, and bird disruption have also been raised in certain areas. That's wind power.
Solar energy can be concentrating the sun's power and using mirrors to heat up water to turn turbines, or it can be using solar panels, and so we're going to look at solar panels and how they actually work. Also, remember that there is something called passive solar energy, which is basically how you face your windows, do you plant trees, how do you insulate, etc.
Solar panels are made up of smaller units called solar cells. The most common solar cells are made from silicon, a semiconductor that is the second most abundant element on Earth. In a solar cell, crystalline silicon is sandwiched between conductive layers. Each silicon atom is connected to its neighbors by 4 strong bonds, which keep the electrons in place so no current can flow. Here's the key. A silicon solar cell uses 2 different layers of silicon. An N-type silicon has extra electrons, and P-type silicon has extra spaces for electrons, called holes. Where the 2 types of silicon meet, electrons can wander across the p-n junction, leaving a positive charge on one side and creating negative charge on the other. You can think of light as the flow of tiny particles called photons shooting out from the sun. When one of these photons strikes the silicon cell with enough energy, it can knock an electron from its bond, leaving a hole. The negatively charged electron and location of the positively charged hole are now free to move around. But because of the electric field at the p-n junction, they'll only go one way. The electron is drawn to the n side, while the hole is drawn to the p side. The mobile electrons are collected by thin metal fingers at the top of the cell. From there, they flow through an external circuit, doing electrical work like powering a light bulb, before returning through the conductive aluminum sheet on the back. Each silicon cell only puts out half a volt, but you can string them together in modules to get more power. 12 photovoltaic cells are enough to charge a cell phone, while it takes many modules to power an entire house. Electrons are the only moving parts in a solar cell, and they all go back where they came from. There's nothing to get worn out or used up, so solar cells can last for decades.
Alright, thankfully solar energy technology is evolving very quickly and the cost is dropping, so I think that we're going to see this more abundantly. You do have to mine for some of the materials, and energy storage and the availability of the sun and location, those are some of our current drawbacks. And lastly, we have to look at conversions quickly and remember the exponents that match up, and try to keep in mind that when we're talking about watts, it's per hour, and so that example up there kind of walks you through it. Remember, if you're going from big or small, or a bigger value to a smaller number, which direction to move the decimal. And so I'm writing small and big for all of them. And so if you're going from a smaller unit to a bigger unit, then that number should actually get smaller, and then vice versa. Alright, so we actually have one more unit, and then we are done with the video. Sorry this one was so long. I'm just trying to prep you for the test. Have a great week. I miss you guys.